In this question, we are required to find the radius of convergence as well. So, which means that we shall use the same method that we used when you're finding the radius of convergence of a power series. So, I'll start by finding the derivatives of this function. F of x is equals to ln x plus 1. So, f0 will be equal to plug 0 in place of x, so that will be ln1, which will just be equal to 0. First derivative of this function, just differentiate it, that will be 1 over 1 plus x. So the value of the first derivative at x equals to 0 will be equal to 1. Second derivative of this function will be negative 1 over 1 plus x squared, and the value of the second derivative at x equals to 0 will be negative 1. Third derivative of this function will be 2 over 1 plus x to the power 3. The value of the third derivative at x is equals to 0 will be equal to 2. The fourth derivative of this function will be equal to negative 6 over 1 plus x to the power 4. So the value of the fourth derivative at x is equals to 0 will be equal to negative 6. The fifth derivative of this function will be 24 over 1 plus x to the power 5. The value of the fifth derivative at x equals to 0 will be equal to 24. The sixth derivative of this function will be equal to negative 120 over 1 plus x to the power 6. The value of the sixth derivative at x equals to 0 will be equal to negative 120. Now, I just want to go back and look at this pattern, the pattern of these guys here. If you can notice anything. In fact, we can just stop at, you don't have to go up to, yep, we can stop up to there. Now, 2 factorial is 2, 3 factorial is 6, 4 factorial is 1. So we can write this, guys, in terms of factorial. So this can be written as negative 5 factorial, 4 factorial, negative 3 factorial, and 2 factorial, which is just 2 anyway. Okay, and we'll use that later on when we'll be plugging these coefficients into the Maclaurin series. And actually, that's the next step. The next step is, remember, we're trying to find the Maclaurin series for this function. Now, the formula for Maclaurin series is here, right? There. So all that we need to do is to plug, we need to plug these coefficients into this formula. So I'm just going to copy this formula into this formula here. So we know that the next step is plug the coefficients into the general Maclaurin series. So we know that the general formula for Maclaurin series is f of x. It's a different color for that. So f of x is equal to f0. So the value of the function at x0, which you know that it's 0. But let me just write the whole expression. X f dash 0 just copying what you have in the formula booklet here. Um, Plus x squared over 2 factorial plus x cubed over 3 factorial. I'll go up to probably, x to the power 4. So that derivative at 0 plus x to the power 4 over 4 factorial, fourth derivative at 0 plus whatever comes next. Okay, so next what I'm going to do is just to plug the coefficients into this formula. So what I'll end up with is f0 is 0. We saw that in the beginning. Yeah, I can show you back again. F0 is 0. Yeah, all right. So, and I'm just going to plug all those coefficients into this guy. So 0 plus x minus x squared over 2 factorial plus 2 factorial over 3 factorial. All right, let me check. So 0 x squared over 2 factorial x cubed over 3 factorial minus 3 factorial x to the power 4 over 4 factorial plus whatever comes next. All right. Now we can simplify this. 0 is just 0. Ignore x plus minus x squared over 2. Now plus this bit you can simplify. 2 factorial over 3 factorial is same as 2 factorial over 3 multiplied by 2 factorial, and those do cancel. Right? That's just how we simplify that. So that will be a third. So instead of writing the factorial, guys, I'm just going to write the fractions that we end up with. So that will be plus x cubed over 3 minus x to the power 4 over 4 plus whatever comes next. All right. So that's basically what it is. But we can go a step further and try to write the general term, the nth term, s sub n, for this series. We can see a pattern here. So start with negatives. So you can start with -1 to power whatever works. Remember, we're starting from n is equals to 0. -1 to power 0 is positive. -1 to power 1. So we can say to power n. And then, so when n is equals to 0, and then we can just have x to power n as well, or n plus 1. Actually, n plus 1 works because you're starting from 0. That way, if you plug 0, then you'll have x to power 1 over where did we start from? 0 factorial is 1, so 0 plus 1. So, yep, we can just write over n plus 1. All right, over n plus 1 will be fine, plus whatever comes next. All right, and if you plug in, starting from 0, this should be able to work. All right, -1 to power 0 is 1, x to power x to power n plus 1. If you replace n in place of 0, then you'll have x to power 1, and then you dominate. So, yep, the pattern works, which means we can write this, we can represent this function as this series from n is equals to 0 to infinity. And here I'm just going to plug in s sub n. So this bit here is actually my s sub n. All right, this is my s sub n. So I'm just going to plug here s sub n. Of course, I won't write s sub n. So just replace that. Oops, with s sub n, which happens to be negative 1 to power n, x to power n plus 1 over n plus 1. Now, I'm going to do something else here. I'm going to change the summation limits. Okay, what I mean by that is I want to change these limits here. The value I want to change from, remember we are starting from n is equals to 0, but I want us to start from n is equals to 1 so that I can simplify s sub n. That's the whole idea. So you can change the limit. So if I want to increase, where to start from. Let me just write this in. If we increase the term we start with by 1, what I mean by that is we have this summation sign. So f of x is equals to, so instead of writing n is equals to 0, I'm going to write n is equals to 1. That's what I mean. So if we increase the term we start with by 1, then what we can do is we can replace n with n minus 1 in s sub n. That's how you change the limits of a summation sign. So we replace n with n minus 1 in s sub n. All right, just write this here. So which means from this bit, use a different color for that. From this bit, I'll end up with this. F of x will be equal to the summation from n is equals to 1 to infinity. And now remember what I'm going to do. Replace. I'm going to replace n with n minus 1 in s sub n. Okay, so which means in place of n in s sub n, I'm going to replace it with n minus 1. All right, so that will be negative 1 to power n minus 1 x to power n minus 1 plus 1 over n minus 1 plus 1. And this simplifies to which is much simpler, because remember, the next step that you're going to do is to use this power series to find the interval of convergence. All right, so it's better if we have a simpler s sub n that you're going to work with. Anyway, I'll carry on. So so we have our Maclaurin series representation of this function. But now we need to determine its radius of convergence. Now, to find the radius of convergence, we are going to use, so next step is to find the interval of convergence. And how do we find that? We use the ratio test. Okay, so you're going to use ratio test, and that's why I was actually simplifying s sub n here. All right, so that it's easier to use ratio test. Anyway, let's carry on. So what you need to do now is we know that our s sub n is now, because you're going to use ratio test, I'm really not going to pay attention to negative 1 to power n minus 1. But anyway, I'll just write it here. So negative 1 to power n minus 1 um, x to power n over n. And like I said, because in the ratio test, we are going to find the limit. We are going to find the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. Okay, because you're taking absolute values, this is really unnecessary, because negative 1, absolute value of negative 1 to power any power will just be 1. So that's why I'm going to ignore it, and I'll just write my a sub n as x to power n. No, it doesn't make sense, but that's what it is. I've just explained why I'm doing that. And a sub n plus 1 will be x to power n plus 1 over n plus 1. Let me just write here. Ignore powers of negative 1. All right, if that makes sense. So what you're going to do now is to plug this in the ratio test, ratio formula, the formula for ratio test. So the limit as n approaches infinity of the absolute value of x to power n plus 1 over n plus 1 divided by x to power n over n, which is equal to the limit as n approaches infinity of the absolute value of x to power n plus 1 over n plus 1 multiplied by n over x to power n, which will be equal to the limit as n approaches infinity of the absolute value of, now this simplifies to x multiplied by n over n plus 1. You can just use your, index laws to simplify those guys, and we can carry on and say this will be equals to, we can factor out absolute value of x, the limit as n approaches infinity of n, oh sorry, that's n over n plus 1, and this is equal to 1. Use LHR, L'Hopital's rule. So this will actually be equal to absolute value of x. All right, but we know that for convergence this should be less than 1, right? For convergence, converges if this is less than 1, which means that our interval of convergence is between -1 and 1. And we need to check the endpoints, all right? So to check the endpoints, I'm just going to investigate what's going on. At x is equals to, let's start with x is equals to -1. Our series will be equal to, so just plug -1 in place of x. So our series will be -1 to power n, -1 to power n over n, which simplifies to the summation from n is equals to 1 to infinity, -1 to power 2n over n, which is same as -1, -1 to power 2n is just, negative. negative 1 to power any even power, it's just 1. So this will be 1 over n. And we know that this is a harmonic series, diverges by P series test. Okay, and then we can also go ahead and find out what's going on at x is equal to, so that, oops, can't see that. So that was at x equals to 1. So at x is equals to, yeah, negative 1. So at x equals to 1, our series becomes, replace 1 in x, so negative 1 to power n, 1 to power n over n, which simplifies this to an alternating series. And we know that this one converges. So it's a different color. By alternating series test. So after checking the endpoints, we can write our conclusion that the interval of convergence is from negative 1 to 1, including 1, right?